So we've now seen what the determinant of an n by n matrix is, and we've seen how to calculate it. I want to prove some more nice properties that determinants have. So remember, very early on we said that if you have a 2 by 2 matrix A, B, C, D, it's invertible if and only if its determinant A, D minus B, C is non-zero. So we want the analogue of this for n by n matrices. So A is invertible, an n by n matrix, if and only if det A is not zero. That's one property we're going to prove. The other property we're going to prove is if I have two matrices A and B, and I take the determinant of the product, I get the product of the determinants. So that's a very nice fact. Makes the determinant a really powerful tool. So let's call these theorems 1 and 2, and let's prove theorem 1 first. So first, we recall that a matrix A is invertible if and only if its reduced echelon form is the identity matrix. Okay. So this is what we're going to use. Now if the reduced echelon form is the identity matrix, then what do we get? Well, to get to the reduced echelon form we used some row operations. So to get from A to the reduced echelon form, we used row operations, and what we've seen is if we do type 1 row operations, the determinant is unchanged. If we do type 2 row operations, the determinant gets rescaled, but it gets rescaled by whatever we're using to do the type 2 row operation. You can't rescale by 0, so rescaled by a non-zero factor. And type 3 row operations, in other words swapping rows, det changes sign. So this tells us that det of A if is non-zero if and only if det of the reduced echelon form of A is non-zero. Right, because these two guys are related by row operations, each of which cannot change the determinant from a non-zero number to a 0 number. It can rescale it by something non-zero, it can change the sign, but it can't make it 0. So we've seen A is invertible if and only if the reduced echelon form is the identity. That says if A is invertible, then det A is a positive or non-zero, let's say non-zero multiple of det of the identity, and det of the identity is 1. So being a non-zero multiple of 1 means you're non-zero. So if you're invertible, your determinant is not 0. The other direction, if the determinant is non-zero, then you're invertible. Well, it's similar. So if A is not invertible, then its reduced echelon form is not the identity, and that means it has to have a row of zeros. Otherwise, if all the leading entries are moving to the right, and there are n of them, then you'd get exactly one in every column, one in every row. So they'd have to live along the diagonal, and you get the identity matrix. So one of the rows has to just consist of zeros if you're not having reduced echelon form being the identity. But then det A is a non-zero. It's a multiple of det of the reduced echelon form, which is then 0. Because if we have a row of zeros, then whatever entry we pick from that row, it's going to be 0. So all the terms in the determinant will vanish. So if A is invertible, the determinant is non-zero. If A is not invertible, then the determinant is 0. So this shows that the determinant really plays exactly the same role for n by n matrices as it did for 2 by 2 matrices. What about theorem 2, that the determinant is multiplicative, so det AB is det A det B? So proof of 2. So we first prove this formula in the case where A is an elementary matrix. This is what we're trying to prove. So if A is Eij lambda, which, if you remember, is the thing with 1s on the diagonal and a lambda in the ij position, 0s everywhere else, then, well, what we're going to do is we're going to compute both sides and check they're the same. So det AB is, I claim this is equal to det B because AB is obtained from B by doing a row operation of type 1. This is row I gets replaced by row I plus lambda row j. Right, remember this is the point of the elementary matrices. If you multiply on the left by Eij lambda, that has the effect of doing this row operation. And we've checked in a couple of videos ago that if you do this row operation, then you don't change the determinant. On the other hand, det A, the determinant of this elementary matrix, is just the product of the diagonal entries, so that's 1. So det A det B is also equal to det B. So just by computing both sides of this equation, we see that the equation holds if A is an elementary matrix. What about for type 2 elementary matrices? So if A is Ei lambda, then det AB is lambda det B. This is because AB is obtained from B by doing the row operation Ri goes to lambda Ri, which we saw changes the determinant by a factor of lambda. And on the other hand, det A, right, this matrix, remember, is the thing with 1s on the diagonal everywhere except II, where it's lambda. And the determinant of that is just the product of the diagonal entries, which is lambda. So det A det B is lambda det B. So again, by comparing both sides, we see that they're equal. So this proves the formula det AB equals det A det B in the case where A is an elementary matrix. By induction, we see that det AB equals det A det B whenever A is a product of elementary matrices. Right. So just applying this same argument and pulling off each elementary matrix at a time, we get this formula when A is a product of elementary matrices. And remember from our earlier work on invertible matrices, this is true if and only if A is invertible. So we've proved our formula for any invertible matrix A. If A is not invertible, then det A is 0 by theorem 1 that we saw just now. So we need to prove, in this case, that det AB is 0, as in it's 0 times det B. And this is equivalent to showing that AB is not invertible. But suppose AB were invertible, then you could write down its inverse, and you could form the product B AB inverse. Right, so we can write down the inverse of the matrix AB, and we can write B times that, and this is now an inverse for A, because A B AB inverse is AB AB inverse, and that's equal to the identity. And that contradicts the assumption that A is not invertible. So that's the symbol for a contradiction. Okay, so it's a slightly odd proof. We work sort of case by case. First we deal with the case where A is an elementary matrix, then with the case where A is a product of elementary matrices, in other words when A is invertible, and then we say, well, what happens if A is not invertible? And we prove by contradiction that in that case det AB has to be 0 because AB can't be invertible. So again, the formula holds. And again, we're just checking the formula by computing both sides and showing they're equal. So you may not yet appreciate why this formula is so great, but I really like this formula, and I'm sure you will come to like this formula more and more as you do more maths. I mean, the point is, this det is given by an incredibly complicated formula, right? This is sum over permutations of products of things with random signs everywhere, and yet it behaves so nicely with respect to matrix multiplication. It's kind of incredible.